Hey everyone, my name is Justin Kruger. I am currently a postdoc in the Space Rendezvous Lab. To give a bit of background, I originally came to Stanford in 2017 to do my master's in aeroastro, and I ended up joining SLAB, sticking around to do a PhD as well, which was mostly focused on this topic here, autonomous angled-only navigation for distributed space systems. So tying into some of the vision-based navigation you guys have been looking at recently. And then after my PhD, I also decided to stay as a postdoc, which is what I'm doing currently with SLAB. So I guess we'll get started. Obviously, thanks for all being here when I'm sure you have lots of project work to be getting on with. But I sort of have divided this into 4 rough sections today. So starting off with talking more generally about the angled-only navigation problem, then going into some of the mathematical models that we use to conduct this in practice, then looking at some specific navigation algorithms from one of the missions the lab has been working on, the NASA Starling mission, and then finishing off with some flight results from that mission. Okay, so to get started, I mean, ultimately to fulfill its objectives, a distributed system in space has to perform some kind of absolute navigation relative to a central body, such as the Earth or the Moon, and has to perform relative navigation within the distributed space system. To basically, before we do anything in space, we need to know where we are. And that encompasses determining the orbits of known or unknown, cooperative or uncooperative resident space objects. And the question ultimately is, how can we navigate multiple RSOs in a way that's autonomous, in a way that's scalable, without necessarily having to rely on something like a GPS system. Because there are many situations in which we can't rely on GPS. Things like space situational awareness, where you're tracking an object that's not necessarily cooperative. Things like on-orbit servicing and debris removal. Things like resilient navigation, so having backup navigation systems that don't rely on GNSS. As well as navigation in like deep space scenarios around the Moon or Mars. Now, in this kind of context, one solution is angled-only navigation, which is pictured on the right here, where you essentially have cameras on observer spacecraft in the system, and they measure the bearing angles, azimuth and elevation, or alpha and epsilon on this slide, to other members of the space system. So you can kind of see an example of the images we might get from the camera in the top right, where there's like a target track of point sources in the center of the image. And mathematically, we can represent this as essentially the unit vector from the observer spacecraft to the target spacecraft, or equivalently as a pair of bearing angles. So I'll sort of go into these formulas a little more at a later point. But a key element of this kind of vision-based system is we are assuming the target is at far range. So it appears as a point source in the image. There's kind of no resolvable features or detail. And that sort of threshold depends on the parameters of the system itself and the camera and the size of the objects, but we can say roughly that if you're more than 1 kilometer from your target, you might sort of see it as basically a point source. So there are some advantages to angled-only navigation in that it essentially becomes pretty self-contained within the system, so your measurements are obtained by the members of your distributed system. You're not relying on something external like a GPS constellation. Cameras themselves are pretty ubiquitous sensors, especially in the form of star trackers. They're pretty accurate, they're low size, weight, power, cost. And we can also navigate for passive targets. So this is an especially important one in the sense if you're trying to track something like a piece of space debris, you can't rely on active sensing such as GPS. You need a passive sensor where cameras are nice because as long as you can see something, you can get a measurement of it. There are some disadvantages, though, equivalently, in that bearing angles don't provide explicit range information. So this leads to some poorly observable modes in the system. And I have a demonstration here where we have an example image. It's kind of a classic optical illusion where you have, in this case, a dog, which in this photo appears to be the same size as the Leaning Tower of Pisa. And the thing is, we can kind of work that out because we have a lot of visual information in our brains about how big dogs are and how big the Leaning Tower of Pisa is. But a spacecraft doesn't have that kind of visual information. So if we replace these things by sort of rectangles, which are featureless, we have a lot less information to work out how far away those objects are. Because Because essentially we're trying to extrapolate distance from an image, which is a 2D piece of information. Now, we can still kind of do this here because we have the background of the image to work with. But again, for a spacecraft, we are generally working with a featureless black background. So this makes our job harder as well. Also, for angles in navigation, we have point sources we're dealing with. So we kind of have these zero-dimensional objects, essentially, we're trying to track. And there, of course, are many objects in the field of view which we have to distinguish, which might be stars and other resident space objects. So our job becomes very difficult. And trying to find the thing we're trying to find is not necessarily easy because we don't have that range information. There are also, as a result, pretty complex dependencies between the quality of the information or the quality of the navigation we can perform and the properties of the system, like the amount of relative motion and the quality of the sensor. And we also have to deal with constraints about optical visibility. So if we're in an eclipse period, for example, we aren't getting any sunlight, we can't see our target, we can't get measurements. So in practice, this essentially means that while there are positives about vision-based nav and angles-only nav, we need some novel algorithms to be able to fully exploit it and actually apply it in flight. So I wanted to talk about this a bit more mathematically as well. So this is kind of an introduction to the classic angles-only observability problem, where our goal is essentially to solve for the relative state vector of our target, which is called C here, some kind of 6x1 vector, which might be position velocity or relative orbit elements. And on the right, we have a kind of a representation of this problem where the target is following some kind of black spiraling trajectory in the reference frame of the observer. And we have these blue measurements to work with, which are the line of sight vectors from the observer to the target. So yeah, we have these vectors L, which we're trying to use to solve for the 6-dimensional state of our target object. And let's assume for now that we know the observer's absolute state through GPS or something like that. So we're just trying to do relative navigation for our distributed space system. So we have a constraint we can work with in that we know that these line of sight measurements are going to be parallel to the relative position of the observer, of the target, sorry, in the observer's reference frame. So if we kind of do the cross product between these line of sight measurements and the observer's relative position, this delta R quantity, we know that this equals 0 because those two things are parallel. We also have this other piece of information where we know that the system is subject to some kind of dynamics model. For example, we could naively choose to apply a linear dynamics model. One that I guess you guys have seen in this class is the linear mapping between the target's relative position in RTN to the relative orbit elements of the target spacecraft, which is shown on the right-hand side there. So we can substitute this in to our linear set of equations, and we can essentially come up with this linear system where we have the components of our various line of sight measurements L and the coefficients of our linear dynamics model, which are the B quantities here. Now, what we find from doing this is each line of sight measurement gives you two constraints which are linearly independent. So each line of sight measurement kind of gives you two pieces of information. And we have a 6-dimensional state we want to solve for, so we can use 3 measurements to, in theory, solve for that 6-dimensional state. The issue that we have, though, is this produces a homogeneous linear system where essentially the solution is like a null space, which you can scale by any amount, and you can still have like a valid solution. So this is kind of the classic angles-only scale ambiguity that everyone has to deal with when trying to use this. So we kind of have this problem where we had this idea, which was very nice, of using low-cost cameras for navigation. We have the bearing angles, which are great, but we don't get range information, which means it's actually, we require additional information to solve for a definite solution. And this can come in various forms. It can be, for example, nonlinearities or stereo vision, but we need something else to work with. Okay, so that's kind of an intro to the problem itself. I guess let me know if you have any questions so far, or just stop me at any point. But otherwise, we will dive into the mathematical modeling side of stuff. So this is, in practice, talking about if we want to apply angle-only navigation, a vision-based system, to enable a future distributed mission, what do we actually need to be able to achieve? So I view this as kind of a three-step process. So we can start with a system design problem where we can develop sort of intelligent design methods which can, ensure a system fulfills its navigation requirements. Since for a given mission we have some kind of requirement we have to meet in terms of the navigation accuracy, and we need some kind of design tool to kind of tackle that from the design stage. We also have then an algorithmic development problem. So once we have designed the system, having a set of algorithms we can apply to actually achieve angled-only navigation in practice for, ideally, sort of general orbit regimes and general distributed system arrangements. And finally, we have this on-orbit implementation problem. So having done these two things, how do we actually practically implement that in the sense of being able to fly it on a spacecraft? So I wanted to kind of start from the system design stage here. And in the context of the state-of-the-art, there are two prior flight experiments that have demonstrated angles-only navigation in orbit. So one is Argon in 2012. This is a mission that Professor D'Amico worked on a lot, which looked at a rendezvous between two small satellites from 30 down to 3 kilometers of separation, which was primarily using ground-in-the-loop-based methods for guidance, navigation, and control. And this was followed by Avanti in 2016, which built upon Argon, looked at, again, a rendezvous between two satellites, this time from 13 kilometers down to 50 meters of separation, with more autonomous elements and doing some of those navigation tasks on board. And the important thing to note is that both of these experiments were very successful, but were also characterized by significant limitations, in the sense that they, first of all, relied on things like maneuvers by the observer spacecraft to help resolve the target range. They relied on having some prior knowledge about the target's relative orbit to initialize navigation. They relied on having some kind of external absolute orbit updates for the observer to maintain convergence. So they did angles only for the target, but they assumed something like GPS for the observer spacecraft. And also, they only applied to a single observer and a single target spacecraft. So they weren't super scalable to future distributed systems. Sure.
What does ground-in-the-loop mean for angles only? Like, were they doing just gathering measurements and all the calculations were done on the ground? Or?
Essentially, yeah. So they took, all the images on board, did some processing and downlinked that processed data, and then passed that into like a ground-based navigation system where they'd compute a navigation solution on the ground, and then do control on the ground and uplink maneuvers back to the spacecraft. Yeah.
Very involved, the mission operation schedule. Basically, we were a team waiting for a ground contact to happen. During the ground contact, all the images that have been collected by Angle spacecraft were downloaded to the ground, and then we started running our software, which was image processing to extract the bearing angles, and then orbit determination, and then maneuver planning, to plan the maneuver commands to be sent to the spacecraft at the subsequent ground contact. That could have been hours later.
Okay.
So really time and human intensive.
Right, yeah. So yeah, while these experiments were successful, those kinds of limitations were something we wanted to actually address through our work at SLAB, which led to the Starling Formation Flying Optical Experiment, or StarFox. So this was proposed and developed by the lab, and is now extending angled-only navigation to 4 satellites instead of just 2. In this case, at much larger intersatellite separations of up to 100 kilometers or so, and is also aiming to do navigation almost entirely autonomously. So StarFox is kind of where we're going, and I want to use the case of StarFox to kind of illustrate some of the system design choices we made, or the modeling choices we made for that mission, and kind of the reasoning behind those, and I guess how they might apply to your own projects too. So I wanted to start with kind of a bit of terminology here just to clear things up. So in terms of some kind of distributed space system, for angles-only navigation, some of those objects are going to be what we call active observers. So that's anything which has a camera on board, which is, getting angles-only measurements. We also say that observers might have an intersatellite link, or ISL, with which they can broadcast these measurements between each other in a cooperative way. We also have passive objects, so these are kind of targets which don't perform navigation themselves, but are tracked by the active observers. And observers are said to navigate for their subsystem. So the subsystem consists of the observer itself, any targets visible to its onboard camera, as well as any remote observers it communicates with over its crosslink radios. So in this situation, we have two active observers, J and M, two passive objects, I and K, and each observer, J and M, they have kind of slightly different subsystems of objects they're trying to navigate for. We can also divide observers into different types. So what we kind of define as a proper observer is an observer that is capable of knowing its own absolute orbit. That's through something like GPS, or could be through something like bearing angles. There are also improper observers, which are observers that can only do relative navigation. They can't do absolute navigation for themselves. So here we come up with sort of the modeling choices we're faced with. Where ultimately, what do we want to estimate and how do we want to estimate it? Actually, maybe it's good to have a show of hands here. Is anyone planning to do vision-based navigation for their final projects for this class? Or is everyone too scared of doing vision-based? It's not that hard, I promise. But look, maybe GPS is simpler. I don't know. So that's true. Just assuming a position velocity solution is quite nice. But okay, I'll talk about some vision-based stuff here, and maybe it'll convince you that actually, you could try using it. Or maybe it won't. Maybe it'll do the opposite. So there are some key choices here where, we have to choose a state parameterization, dynamics models, measurement models, and a filter architecture. And all these choices kind of have pros and cons. A lot of the time you run into this issue where you want an efficient model to run on a spacecraft, or you want an accurate model to give you the best results, and often those two things are kind of conflicting. In general, I sort of view this as like a four-way trade where some things are very easy to use and easy to implement. Some things are sort of more intuitive to think about in like a geometric way, for example. Some things are more efficient, some things are more accurate, and in general, there's kind of no right or wrong choice here, but each will have its own advantages. And let's use Star Fox as an example to see what we define for that and how that relates to the goals of the angles-only navigation system. So first we have the state parameterization. We say that for Star Fox, each observer is estimating its own absolute state and the state of n targets. And there are plenty of choices you can make here, Cartesian or orbit element states, osculating or mean orbits. The targets especially are sort of interesting because you can estimate the absolute or the relative state of a target. You can also estimate it in an inertial frame, or you can try estimating it in like a rotating frame. For the choice of Star Fox, we do quasi-non-singular absolute orbit elements for the observer and quasi-non-singular relative orbit elements for the target. In terms of the orbit elements, one of the big reasons was that we can do more efficient propagation using the GVEs and numerical integration. We also have lots of analytic models for propagation also, for the orbit elements in particular, so that helps us as well for the efficiency problem. We have a lot of geometric intuition regarding target relative motion, especially for the ROEs. I'm sure you've kind of gone through the familiar diagrams of ROE motion in the RT and RN planes, and sort of how that maps very nicely to the different integration constants. Now, the issue we kind of have is that our measurement model, being as it is sort of based on, say, the unit vector of the target in the observer's reference frame, or kind of the bearing angles, we need Cartesian information, or the Cartesian positions of our target and observer to actually compute that. So we kind of need an extra operation to go from the orbit elements to that Cartesian space for our measurement modeling, but it's kind of a small price to pay, I think, for the other advantages here. So the next thing is the dynamics model, propagating the current state into future epochs as part of the navigation filter. Again, plenty of choices here, whether you want to do this analytically or numerically, kind of how many perturbations or how much detail you want to include in your dynamics. So for Star Fox, we choose numerical integration of the Gauss variational equations, or the GVEs. And we do this for the absolute orbit of all the objects. So that's both the absolute orbit of the observer and the absolute orbits of the various targets. So even though the target states are ROEs, we sort of move them back into absolute orbit space for the propagation. Kind of the reason for doing this is that it's kind of nice to have one dynamics model that can be applied to the observer and the targets for consistency. And the operation to convert from orbit elements to relative orbit elements is, again, very cheap. So we do orbit element propagation. The GVEs are, again, great for being able to include arbitrary perturbations and kind of improve the accuracy of your modeling without too much computational cost. Another note is that there are some parts of Star Fox in which we require very fast propagation. And for that purpose, we do use an analytic state transition matrix for either the orbits, the absolute orbit, or the relative orbit of the targets. So this is kind of a backup option here, in that it is much less accurate, but it is much faster when that is needed. And in this, we include the effects of J2, which is kind of the largest perturbation we have to worry about for Star Fox, since it's kind of a low Earth orbit, and the altitude is kind of high enough that we don't have to worry about drag too much. Okay, so next is kind of the measurement model, which is perhaps the most important here in terms of the definitions. In terms of the choices, I mean, there isn't really too much to work with. For simplicity, I'm going to assume the observer has access to GPS or some kind of external source which allows it to know its own absolute orbit. But for the target, we've kind of already chosen that we're going to use camera images for navigation, which give us the target line of sight vectors or bearing angles. So to do this, we do need to define some key coordinate frames. First of all, the frame in which we're actually doing estimation, which in this case is the Earth-centered inertial frame. We also have the frame in which our measurements are obtained, so this is the frame of the camera. And we need to be able to relate those two things together. So how to kind of map information we get in the camera frame to doing our estimation in the inertial frame. So to define the camera frame, we have this figure on the right where the camera frame consists of 3 unit vectors for the 3 axes, x, y, and z. And what we kind of define as the sort of how we lock our camera frame to our specific estimation scenario is we align this sort of z unit vector with the bore sight of the camera. So essentially it points out of the plane of the image. And we can then align the x and y unit vectors with, say, the horizontal and vertical pixel coordinates of the image, or whichever kind of choice we want to make there. We also have the inertial frame, x, y, and z, which in this case is sort of the J2000 frame. And we then need to be able to kind of take measurement information from the camera frame and put it into the inertial frame. So here, specifically looking at the definitions of the measurement model, we have the line of sight vector, which is like a 3x1 vector, between some observer I and a target J, which we can define here as the difference in position from the position of the target with respect to the observer, and then turning that into a unit vector. Now, equivalently, we can define a bearing angle made up of azimuth and elevation, which can be computed from this unit vector. Bearing angles can be preferable in the sense that the unit vector is 3D, the bearing angle is a 2-dimensional or has 2 components, so it's a little more efficient in terms of how we store our information. And we then have to relate these camera frame unit vectors or bearing angles into the inertial frame, which is typically done through some kind of rotation from the camera frame to the inertial frame, which can get applied to those camera frame unit vectors. So it's kind of worth, I guess, talking about how you might be able to get that. In many cases, the satellite bus itself might have an ADCS system which provides that rotation matrix or quaternion automatically. We can also do it ourselves and estimate our own attitude from the same image we're using to track our target spacecraft. So very briefly, you can use something like the pyramid algorithm to identify the stars visible in your image. And then you can kind of compare the the unit vectors to the stars in your camera frame to the unit vectors of the stars in the inertial frame from some kind of catalog, and solve for the optimal match for the rotation, which makes those two things match up. So it's a fairly straightforward operation, which lets you get this rotation, this attitude, from the same image you're using to get your target spacecraft measurements, which is nice. And we can represent this as a rotation matrix or a quaternion, sort of as you prefer. So in practice, I sort of haven't talked about the image side of this yet, even though this is technically, a thing about vision-based navigation. So in practice, you have to extract your line of sight vectors from an image which is made up of pixels. So here's an example of a typical star tracker image from the Star Fox experiment, actually, where you can see a bunch of objects which are just point sources, and these have been classified by the image processing system. So the yellow ones here are stars that were identified using that pyramid algorithm I mentioned. There are some red objects which are currently unidentified. And the two green objects in kind of the top left are two of the target spacecraft in the swarm. So what we can do is we can apply some centroiding algorithms to this and get the pixel locations of those two swarm objects. And then we can apply a camera model to extract the unit vector information. So this is kind of the simplest model you can do. It's called the pinhole model, where on the right-hand side, for example, you have your two pixel coordinates, px and py. And if you know some information about your camera, such as the focal lengths and such as the cx and cy quantities, which are like the coordinates of the central pixel, you can extract these capital X, capital Y quantities, which are essentially, where your line of sight vector to your target is kind of intersecting with the plane of your image. And in doing so, you can solve for your unit vector and your bearing angle. So again, it's kind of, taking this idea where you have a 3D relative position vector for your target. It's kind of passing through this 2D image plane, so it's reduced down to 2D information. Okay, so this is kind of a quick recap of, if you wanted to actually implement this, what would you have to do? First of all, you need a way to get from your state to your measurements. So to do this, you need your camera attitude, or your rotation matrix from your inertial to your camera frame. You need to know your observer's inertial position vector from your simulation, for example, as well as your target's inertial position vector. You can compute the line of sight vector to your target. You can convert that to bearing angles, and you can rotate it into the camera frame as you need to. Likewise, you need to know how to get from the image to the measurements we're using. So we have some kind of input array of pixels, depending on the parameters of your camera. You need to know some of those camera parameters from the previous slide, such as the focal lengths. And then it's pretty straightforward to compute the pixel location of an object, convert it to the line of sight vector, convert it to bearing angles, and compute the camera attitude. Noting that, I think if you wanted to implement this for a class project, you don't necessarily need to worry about this whole image layer. You can kind of just start from assuming, I've got unit vectors or bearing angles to my target in the inertial frame, and just work with those in a navigation filter. That's kind of the most straightforward way to do this. So that's kind of an intro to the navigation problem and the modeling choices for Star Fox. I now want to kind of go through a couple of the specific algorithms we developed. So this is kind of, I guess, getting more into the researchy side of stuff here. But yeah, it's first worth talking about the idea of the navigation architecture, where a complete sort of navigation system is going to consist of several integrated algorithms which each provide some necessary capabilities. It's not just a navigation filter on its own. It's going to be a whole set of algorithms here. So we start off by pointing a vision-based sensor at some kind of region we want to image. We get the images. We have to do this image processing step to get bearing angles for our targets. We have to do some kind of data association step. So this is where we have to take those angles and actually be able to match them to targets we're tracking. Doing then batch estimation. So if we have a set of bearing angles, can we use them to initialize the state estimate of a target spacecraft? And finally, then doing some kind of sequential estimation. So taking that initial estimate and refining it over time, which is probably where your navigation filter would come in. So we can actually then, use that state knowledge to achieve mission objectives. So this is actually quite a lot of stuff to fit in a single star tracker, but it's kind of what we try to do for Star Fox. And we keep trying to put more algorithms in there. So this is an ongoing problem. So the thing we developed for Star Fox is actually called Artemis, or the Absolute and Relative Trajectory Measurement System. This is not to be confused with NASA's Artemis Moon program, even though it frequently is. I actually don't know which came first. Probably NASA's thing, I imagine. But we have this Artemis thing where we deploy it on one or more cooperative observers to track one or more non-cooperative targets. A kind of a nominal kind of Artemis system consisting of 4 spacecraft is shown on the bottom here, where key features are that it is angles only, so it uses the cameras on board each spacecraft, in this case star trackers, to image other swarm members. The idea is that it's distributed, so different spacecraft in the swarm might be estimating a different subset of the complete swarm state. It is cooperative, so the observers have cross-link radios they can use to share measurement information with each other. It's autonomous, so requires minimal external interaction. In theory, we don't need GPS to run this. And is miniaturized as well. So another thing we wanted to do is kind of make it suitable for small spacecraft hardware. In this case, trying to run it on like 6U CubeSats. So this is kind of a rundown or like a summary of the various states and measurements we're applying to Star Fox. This is kind of a repeat of stuff you've seen before, but there's a couple of things to point out. One is that we're not just estimating the orbits of the various targets, we also estimate these kind of optional or auxiliary state components. So these are things like empirical accelerations or like the unmodeled perturbations acting on each spacecraft. They can be sensor biases, they could be drag coefficients, they could be even like the clock offsets between different observers in the swarm. So all this stuff, the most basic thing to estimate is just the orbit elements. But typically, all these other parameters are going to affect how you model your system in your filter and the ultimate accuracy you can achieve, in the sense that you might think you sort of know some of these parameters a priori and you can kind of provide them to the mission from the ground. But often that data won't be perfectly accurate, so being able to estimate them online is definitely a boon for long-term autonomy and robustness. And in terms of the measurements, it's the main stuff is again the bearing angles per target, as well as the quaternion relating the sensor to the inertial frame. Okay, so this here is kind of a block diagram of the Artemis navigation architecture for angles-only navigation. So the goal here is, robust and accurate vision-based navigation for autonomously localizing multiple agents applicable to both Earth orbit and deep space. And it's divided into 2 steps here, where on the left is like an initialization step, where given like no prior information about the target, how do we compute an initial state estimate? And on the right is a refinement step where we want to refine that state estimate over time. And there are also 3 core algorithms in red, blue, and green here. So we have an image processing step, which is the red in IMP. We have this blue step, which is batch orbit determination, or BOD. And we have this green step, which is a sequential orbit determination, or SOD. And I want to give sort of a super quick rundown at a pretty high level of like how each of these things operates and some of the more interesting, I guess, mathematical principles behind them. So let's, I guess, start with image processing. So the goal is to produce batches of bearing angles to each visible target using a sequence of images from the onboard camera, as well as a coarse estimate of the observer's orbit at one epoch. So we need some kind of rough idea of the observer's orbit, but we don't need kind of extended orbit information over time. And in low Earth orbit, the IMP algorithm runs about once per minute. So sort of as a rough rule of thumb, Artemis expects like around 100 image measurements per orbit to operate nominally. So here's kind of a flow chart of what image processing is doing, where we start. Oh, go ahead.
I was just wondering, would it be possible to get that course estimate outside of GPS? Like, could you do vision based on looking at the Earth or something?
Yeah, you totally can. So if you have a model for the Earth, you could say look at land masses and say, okay, this is what it appears like in my camera frame.
Yeah.
I have a bunch of unit vectors to features on the Earth instead of like spacecraft, and I can kind of back out my own position. This is actually an active research area in the lab at the moment where one thing we can do, for example, is take an image and we have unit vectors to other resident space objects, like random satellites passing through the field of view. And if you have like a catalog of where those satellites should be, you can kind of compare that to your image and back out your own position, which is not necessarily like a trivial problem. It's like a pretty big search space to work with, but it's a way you can, in like a lost in space way, try and initialize your own position estimate. So yeah, it's one of the things we're doing right now is trying to remove that requirement for needing some idea of your own absolute orbit to start the system. It's a good question. I think the catalog is obviously, more similar to the existing angles-only problem. Whereas if you're doing Earth imagery, maybe you have to have some kind of like ML-based layer to like recognize, oh, this is like Africa I'm looking at, for example. But I think they're totally kind of similar systems which should work equally well, put it that way. Yeah, thanks for the question. But yeah, I guess in the context of, this image processing layer, we take the images and we classify the various objects in them using star identification algorithms, using like noise and clutter removal. And the idea is that we're left with a set of bearing angles to unidentified objects in the field of view. And these could be the spacecraft we're interested in, or they could be arbitrary objects. The question then is like, how do we actually map these unidentified vectors to potential targets? And we apply an approach called multi-hypothesis tracking, which is essentially looking at all the possible ways we can connect these different unit vectors into tracks for targets and propagating those over time. And I'll go into this approach a little more in the next slide, but the idea is that it's quite robust, but is also costly in a computational sense for a spacecraft. So what we kind of do is we say we have a good idea of how sort of swarm targets for the context of Star Fox should be behaving in the frame of the camera, in that they should have these closed relative motion ellipses based on, say, relative orbit elements. And we can use these expectations to kind of choose the most likely hypotheses for how these angles are getting assigned to targets. So this multi-hypothesis based approach lets us create possible target tracks, even if we don't actually know anything about the relative orbits of a target. Having said that, if we have the relative orbits of the target, we can use that state information to predict where the target's going to be in the image and much more easily do that measurement assignment step. So here is kind of a quick rundown of multi-hypothesis tracking, since this multi-target tracking problem shows up a lot in navigation contexts, where you have sensor data which can be fairly sparse. You have lots of potential targets that can be swimming around in this area of interest, and how do you actually create tracks for those different targets? There are many possible algorithms to work with here. A couple are Global Nearest Neighbor, or GNN, JPDA, which I think is Joint Probabilistic Data Association, etc. The one we chose to do for Star Fox is called MHT, or multi-hypothesis tracking, and really the idea is you maintain multiple hypotheses of how you can assign things to different tracks. So there's kind of a representation on the right-hand slide here. So in the top right, for example, you have two tracks like T1 and T2, and they each have like 4 measurements in them, which are the 4 crosses. And based on those past tracks, you have these predicted positions, P1 and P2, in like the current time step. And also in the current time step, you have these 4 black squares, like M1 to M4, which are possible measurements you got from your camera, for example. And what we do in multi-hypothesis tracking is we sort of don't say, okay, M1 is assigned to track 1, and we kind of just start branching off hypotheses, saying, okay, we could reasonably assign M1, M2, or M3 to track 1, so let's split off into different trees or hypotheses, and in each hypothesis assign a different measurement to the track. And we kind of do that for all tracks, all possible targets. And basically the idea is that, over time, as you get more information about your track's motion, you can make better decisions about which track is actually correct, and use that future data to disambiguate difficult choices in the present. So this is kind of a provably robust approach in the sense it's been deployed in the real world. It's pretty common. The issue is that the computational cost scales very poorly. So if you have a lot of measurements in close proximity, if you have a lot of targets, as in like the bottom right, you get this really rapidly growing tree of different track possibilities, and that's kind of hard to deal with, especially for something like Star Fox, where it's like a pretty low-powered CubeSat processor. So to address this, we created something called SAMUS, or the Spacecraft Angles-Only Multi-Target Tracking System, where the goal was to, take some of the lessons from those past angles-only flight demonstrations called Argon and Avanti, take some of the benefits of like more naive multi-hypothesis tracking, and combine those two things to create a tracking algorithm that could deal with our specific kind of in-space context and be very precise and very efficient. So really the core of SAMUS is that it does a lot of stuff with kinematic modeling of target orbits, which really kind of stems from the linear dynamics models you guys have looked at in the class, mapping the relative orbit elements to relative motion of a target in the RTN frame. So here is an example of one of these maps. It's kind of slightly expanded from the usual one to allow for arbitrary orbit eccentricity. But in essence, this map, we have the RTN position of the target on the left, and this gets mapped to the relative orbit elements on the right. And we have this kind of parametric curve defined by the observer's orbit and the target's orbit. And the kind of parameter of this map is F, which here is the true anomaly of the observer spacecraft. And that's kind of the only quickly varying term in this map. All the other terms are pretty much constant or slowly varying due to perturbations on like the scale of several orbits. So in the context of angles-only navigation, we are interested in the elevation angle and the azimuth angle. This kind of maps to these two sort of subcomponents, where on the bottom we have the azimuth, which is related to, in this case, the motion in the normal direction or the cross-track direction. And we have the elevation angle, which in this case is related to motion in this kind of x direction, this radial direction. Now, there are some neat things we can do with this, in the sense that we can actually form linear systems from this mapping, where, let's say, we have a track that we have a hypothesis about. We can separate this linear map into components in azimuth, components in elevation, where on the right-hand side of these systems, we have the measurements in our track hypothesis, so just the list of bearing angles in our track. On the left-hand side, we have all these terms in the mapping, and this is all the stuff that just comes from the known absolute orbit of the observer spacecraft. And we have these quantities y, which is what we can solve for using this method. And these y quantities are essentially just scaled equivalents of the relative orbit elements in like bearing angle space. So given like 3 measurements in a track, we can solve this system. We can come up with sort of a motion for what the ROEs are in the sense of the bearing angles we're observing. And that means we have very quickly a model we can use to kind of assess and predict target motion with. Even if we know nothing about the relative orbit elements themselves, we can kind of solve for approximate versions of them using just the bearing angles. And another neat thing we can do is that we can, using this map, say we have expectations about how targets should be moving. So we often sort of have this, roughly elliptical representation or expectation for target motion, where we can say, okay, given this expectation, we expect targets to not be, or sort of have a maximum velocity threshold in the camera frame. We expect their velocities to be like relatively consistent over time. We expect this track to like turn gradually in a consistent direction over time. And we can also say like the new measurement we expect is close to our predicted measurement. So by applying these various kinematic rules, we could develop ways to like mathematically say this track is physically unreasonable or this track is kind of the best one we have. And use this to filter out our multiple hypotheses and more effectively arrive at the correct choice. I think this is an example video actually of how this kind of operates, where we have like 3 targets in the field of view. As they get close to one another, you get lots of weird hypotheses forming for like how they might be arranged into different tracks. But then over time, as you get more and more measurements, the system realizes, hey, okay, I should be kind of following an elliptical path. Let's trim the tracks which don't fulfill that expectation. So obviously, this is kind of an idealized example, but in principle, you can tune your algorithm to be able to deal with more targets, more sort of unusual motion, more sort of camera noise, and be able to do this measurement assignment stuff without knowing anything about the relative orbit elements themselves. Sure.
Is there like a grid space in this that it's looking at? I guess I might have missed that part of the talk, but it kind of looks like there's a grid space here.
In this case, no. So it's not sort of looking at like a discretized search space in that sense. This kind of is a grid space in that it's like the pixels of the image, but the bearing angles can be like anywhere mathematically, and we can still just apply the rules in like a continuous sense. Yeah. Okay, so the next thing here is batch orbit determination. So the idea then is to take these bearing angles from image processing and to essentially use them to compute an initial orbit estimate for our target object. So it's kind of, I think, worth going back to this initial angles-only scale ambiguity problem where we found that, in theory, the range to our target might be unobservable with bearing angles alone. But there are ways we can try and get around this. So one possible approach is to, previously we kind of substituted a linear dynamics model into that system. We can instead derive something like a second-order dynamics model. This is something that Matthew Willis did as part of his PhD in SLAB, where he took that linear mapping and added second-order terms. And what we find is that if we substitute this into that system of equations, we get like a quadratic system instead of a linear system. And this quadratic system can give us definite solutions for the relative orbit elements, including the target range, if you're able to solve it. So the idea then is that if we have second-order information and we can take that into account, we can get the observability we need for angles-only navigation. And that is partly applied in the batch orbit determination system here. So the way it kind of works is we have this batch of bearing angles, z, which is across a set of epochs t, and it's dependent on the system state x at some time. We know we have this sort of observability problem with our bearing angles, where the same bearing angles might be a target close to the camera, moving very little, or a target that's far away with more relative motion. And what we kind of do here is we define an initial relative orbit element estimate, x, and we define a set of samples of delta lambda. So we say that we think delta lambda, the ROE sort of delta lambda is anywhere between like 0 and 500 kilometers, and we kind of sample that window. In this case, delta lambda is kind of the relative orbit element which most corresponds with that weakly observable range component, and was sort of the long track separation between the spacecraft. And for each of these delta lambda samples, we compute this quantity delta z, which is essentially the difference between the bearing angles we got from the camera and the bearing angles that we can model based on our current state estimate. So we get this kind of measurement residual, which tells us how accurate our current state estimate is. And over time, we can say iteratively update our state estimate to try and reduce that residual and more closely match the angles we got from the camera via least squares, for example. And really the goal is to produce a plot like this one on the bottom left, on the bottom of the slide here, where on the x-axis we have the delta lambda samples, and on the y-axis we have these delta z like measurement residuals. And we can pick as our output the delta lambda sample that produced our minimal residual. And the nice thing here is that we're kind of exploiting the relative orbit elements. This is something that comes up a lot in this class, where there are many ways you can like represent the state of a system. Often the one we like to do is a Cartesian state, because we all are very familiar with Cartesian states. But here we can kind of exploit the relative orbit elements and say, if we separate out delta lambda, we can use different estimation techniques to handle delta lambda, different estimation techniques to handle the other ROEs, and be able to actually solve things in that way, which lets us do something we couldn't do if we were using just a Cartesian state. So this is why it's often worth keeping the ROEs in mind for various problems like this. I'm going to skip this and move on to sequential orbit determination, sort of the last element of the system here. So the goal then is to, we've got the state initialization. We now want to actually refine it over time, using bearing angles from the camera, as well as bearing angles that could be broadcast by other observers over that intersatellite crosslink. So at its core, SOD relies on an uncentered Kalman filter for this. I want to kind of go into like why we made that choice. We can use the filter to estimate our state. There are plenty of choices here for like what filter you can actually use. In general, Kalman filters are not super useful for our context because they're only for linear systems. A very common choice for spacecraft is the extended Kalman filter, which is sort of like a first-order approximation of the nonlinearities. Another sort of more common choice these days is the uncentered Kalman filter, which can incorporate some higher order information up to third order, as well as stuff like a particle filter, which can capture like arbitrary and non-Gaussian behavior. However, we have a lot of concerns in that we have the angles-only problem, which is only weakly observable. We also want to run this on board a spacecraft. And let's say we can reasonably assume like a Gaussian probability. So in this context, a UKF is a pretty good compromise between accuracy and efficiency. Okay, back to this old slide again. So there are also other ways we can solve this issue with the angles-only observability. One other option, which we also apply for Star Fox, is we don't just use nonlinearities, we use the fact that we have multiple observers available to us. So another possible approach is if we have multiple observers and we kind of know their locations, we can essentially triangulate the position of a desired target. So, we have these two unit vectors, we know they intersect at some point in space, and we can geometrically solve for that via triangulation. So this gives us a lot more geometric information to work with. So broadly, the UKF here applies the orbit element states we talked about, applies the nonlinear dynamics and measurement models. We can also do some neat stuff with like how we organize the state representation to reduce the number of calls to, say, an orbit propagator when actually running the filter. And we can make essentially, again, choices where we leverage the relative orbit elements in some way to improve our efficiency. If multiple observers are available, we do the distributed stereo vision approach, keeping in mind that this means we need algorithms to make sure that if we have measurements from different observers of the same target, we're like correctly matching them within the filter. So that requires some extra steps. And there are also some other things here, things like adaptive process noise estimation, auxiliary state estimation, which help improve the overall autonomy of the system. I have a quick slide here on the uncentered transform. I believe Simone has already kind of talked a bit about this, but it's kind of the core tool of the uncentered Kalman filter. There are different ways you can compute the uncentered transform. In essence, you're taking a probability distribution, you are sampling from it, generating things called sigma points. You are passing them through some kind of nonlinear mapping, and then you are taking those mapped points and converting them back into a probability distribution. So it's kind of this mathematically rigorous way of moving or passing a probability distribution, such as your state estimate and covariance, through some kind of nonlinear model. This is kind of the way we specifically do it within StarFox. If you sort of wanted an example of, one way to implement this, but there are many ways you can kind of choose sigma points in the literature, how you can weight them, and so on. But ultimately, what we want to do for SOD is an uncentered Kalman filter, which has various components. So we kind of start off from the top left here, where we have our state and covariance at some time. We then do the uncentered transform to generate sigma points, and then we do the filter prediction. So to every sigma point, we pass it through our orbit propagation. And we have, now at this point defined all the various tools we need to actually do this. So for our dynamics model, we have the GVEs. For the control inputs, we, for example, have control matrices. We then have the updated state estimate, which also requires us to have a process noise model. In the case of StarFox, we define the process noise in the RTN frame as kind of these perturbing accelerations to the spacecraft state. So we then have done our prediction step in the filter. We can then again do the uncentered transform, and then do the predicted measurements of all of our sigma points through this bearing angle measurement model we defined. And we can do that to use that information to update the state estimate that we have, where again we require some kind of measurement noise model. For StarFox, we kind of apply around 20 arc seconds of noise 1 sigma to each of our azimuth and elevation angles. So in theory, this is actually like how StarFox works. And given the sort of UKF framework and given these sets of measurement and dynamics models, you can pretty much implement it in a reasonably straightforward way. Okay, the last sort of 10 minutes I have here are just cool videos. So that's all the math, I think. I don't know if this is going to work.
Groups of self-coordinated
it does.
spacecraft, also known as swarms, will open the door to exciting new opportunities in science and space exploration. NASA's Starlink mission is a key test of the technologies that will make this vision possible. Starlink consists of 4 identical small satellites. With Starlink, the goal is for a swarm to cooperate and work as one, with minimal human intervention. From Earth orbit, automated decision-making systems take the place of ground controllers, performing tasks from determining the relative positions of the spacecraft to planning and executing maneuvers. These types of operations are impractical to manage from Earth when a group of spacecraft is large or when a swarm is so distant the time delay for communications is significant. The mission also has an experiment that monitors Earth's upper atmosphere, with the onboard systems autonomously choosing which spacecraft is best positioned to make observations. Starlink's technologies will help realize a future where groups of spacecraft are able to work together on their own, whether close to home or far away.
Okay, so this is, kind of the primary motivation behind a lot of the development of this angles-only navigation stuff was this mission called Starling, which was developed by NASA Ames and consists of this swarm of 4 6U CubeSats in low Earth orbit, launched in July 2023. And for StarFox, we use the onboard star trackers and crosslink radios to do absolute and relative navigation. Specifically, you can kind of see the Starlink satellites in the lab on the right there, where they each carry 2 star trackers, software-defined radios, a Q7S payload processor, which is like around 700 megahertz clock speed, GPS receiver if we need it, and 4 thrusters as well. So 2 examples of like the results we have from StarFox here. The first is looking at the autonomous initialization idea. So using the IMP, like multi-hypothesis tracking, to generate target tracks, then passing that through the batch orbit determination system to generate the initialization, and then doing the sequential orbit determination to refine that state over time using new images. So here is a video where on the left here you can see images from the onboard star tracker, and these are getting passed through image processing, which is classifying these various objects, where the yellow are kind of stars that are identified, the red ones are unknown for various reasons, and the two in the white circles here, which are like, or the green squares, are the two swarm members that are actually being tracked by the system. So for the first roughly 5 or so hours, I think, of the simulation, it's doing the independent multi-hypothesis tracking. So IMP is trying to connect these bearing angles into tracks. This then gets passed to the batch orbit system, where you can kind of see that the delta lambda estimate it's producing on the bottom right here in red, where you can see like this estimate is like around 80 kilometers of intersatellite distance. And in the top right in the blue, you can see the relative position error and uncertainty of the target's relative position in the RTN frame of the observer. A couple of things to note are that you can kind of see the most uncertainty is in the tangential or along track component, which again is like, roughly corresponding to that range component. We can't really observe that well, so that's pretty much expected. Whereas the other two components are much more accurately estimated. We are also able to do this in the presence of pretty big measurement gaps. So on the right, the sort of vertical gray shaded regions are where we're actually getting new images. So we have pretty frequent long gaps for various reasons, such as eclipse periods, and we're able to keep estimating through that. And yeah, overall, we kind of achieve angles-only nav performance of the uncertainty being around 1% of the intersatellite distance. Okay, another example here is sort of a more ambitious example, actually, where this is the kind of multi-observer, multi-target demo, where we have several spacecraft doing angles-only navigation and sharing bearing angles with each other. The thing of note here is that if you have multiple observers in the system, you get enough observability to not only do relative orbit determination, but also absolute orbit determination for the various observers. So this means you can navigate long-term without GPS, essentially. So in the top left, you can see kind of the relative orbit geometry of the 3 involved spacecraft in this experiment, where anytime there's like a black line that flashes, it means there was an observation between those 2 swarm members. At the top, again, you can kind of see the images from the star trackers. And below that, in the green, you can see the absolute orbit estimate of one of these spacecraft, SV4, where it starts off from like a pretty coarse initial position. We kind of artificially degraded this to give you around, say, 8 kilometers of initial orbit uncertainty, which the system can then refine over time just using the intersatellite bearing angles and vision-based measurements. And it's still, the observability is still pretty challenging here, so you can't refine it super fast, but over time we can maintain that orbit estimate pretty well. And below that, you can see the relative orbit estimates of 2 targets. Again, the RTN position uncertainty, where compared to like a typical single observer case, this is slightly improved. Because again, we get much more geometric information from the multi-observer system. I'll skip over this, except to say that, as part of the mission design process, we defined various performance requirements pre-flight, and in practice, we're able to achieve pretty much all of these through the system, which was great. And this also provided a lot of first kind of demonstrations of various types of angles-only nav. The simultaneous multi-target, multi-observer stuff, this initialization on board using the autonomous batch orbit system, as well as not having to do things like maneuvers to actually resolve the target state estimate. I think the last couple slides here are just kind of some interesting lessons from trying to do this in practice. So one thing was that the visibility of the target spacecraft was a lot worse than we expected. We kind of had planned to be able to see targets at distances of up to 200 kilometers. In practice, anything over like 120 kilometers away was pretty much invisible. You can kind of see an example of this here where spacecraft SV3 is pretty reasonably observed, whereas spacecraft SV2 is dimmer and farther away and is only sometimes picked up by the image processing system. Another aspect is sort of the testing side of things. So something the Space Rendezvous Lab pays a lot of attention to is having these kind of test beds which can emulate something like a vision-based sensor and be able to test an algorithm with actual images from like a camera in the loop. So we could do this during like the development of all these Star Fox algorithms, but not actually after the algorithms and the cameras were kind of integrated with the spacecraft. And so a lot of stuff couldn't really be tested after the integration step over at Ames, which led to a lot of sort of issues here and there. A couple of examples are that we had a desynchronization of like the time between the star tracker and GPS time. So the time of the star tracker images was kind of a few hundred milliseconds behind the real time. And if that happens, you get a pretty significant state bias in that your navigation filter thinks your targets are like 200 milliseconds behind, and that manifests as like a several kilometer offset in the along track direction. So you get these kind of issues where you wouldn't necessarily think, okay, that timing is something I have to test or verify beforehand, but it proved to have a very significant impact in practice. It's something we often assume in that we'll have correct time on board, but it's not necessarily the case. However, one thing that was very useful for being able to actually have a successful mission in these difficulties was having what is often called a digital twin of the flight software. So having a copy of the flight software on the ground where we could record all the inputs that we got on the spacecraft, download them, play them back on the ground, and very quickly replicate what was actually happening on board. So it was very useful from like a troubleshooting perspective and being able to kind of quickly respond to all of these various problems. Okay, I think ultimately, so space is really hard. The Starling swarm consists of like 4 different spacecraft: SV1, SV2, SV3, and SV4. SV3 is currently, who knows what's happening with SV3 actually. SV1 is like very sick. It's currently being treated as best we can. And really SV2 and SV4 carry this whole mission on their backs, so thanks to them. But spacecraft, they don't operate perfectly. They always break. So having good problem-solving skills, planning for adaptability in your software is kind of key for doing this in practice. SV1 had a propulsion leak at first, and that was fixed. And it also has a radio problem where the uplink is really slow. So we can't like send commands to the spacecraft really. Or the way we have to do that is you send like a command to SV2, and SV2 sends it to SV1 via like the crosslink radio and not like the ground radio. So it's like a whole network problem, So it's like usable kinda, but like if we wanted to update the software on SV1, that's like a whole deal. So yeah. And yes, in summary, angles-only techniques are compelling, I think, for enabling distributed space systems. But really the problem is that angle-only navigation is very weakly observable. So you have to take that into account at kind of every stage, from like the system design to your image processing to your orbit estimation algorithms. Having said that, Star Fox has provided a lot of the first demos of this acting in sort of more general scenarios. And there are many current research directions being explored, extending this to like cislunar environments, doing tracking of not just the swarm, but of resident space objects, as well as I talked about a little bit earlier, using visible like passing satellites, catalog objects to try and do better positioning of the observer spacecraft. So yeah, that's all I have. Thanks for your attention. Happy to take any questions.
Partially autonomous. What does that mean?
Yeah, it's sort of, there are varying degrees of autonomy, right? In the sense that Star Fox is like, once you initialize it, it's essentially autonomous. In the sense it can do absolute and relative nav using just angles. but it does need some kind of initial ground contact to like initialize its orbit estimate. So in that sense, it's kind of autonomous once you get it going, but not entirely autonomous. So the hope is always to like, keep moving in the autonomous direction to make that more autonomous in the future.
Right.
Yeah.
So the catalog didn't work.
Exactly. Yeah. Yeah. Sure.
I had a question because for your dynamics model, you said you were doing numerical integration and had an SVM as a backup, or
Yeah.
when you needed to go for the filter or whatever to go faster, when would that kind of situation would like arise?
Yeah, it's actually a good question. It's something I skipped over here. So the numerical integration is happening in this UKF all the time. Whenever we use the state transition matrix, it's in the batch orbit determination initialization, because we're doing this sampling approach with the delta lambda samples, and so there could be like hundreds of those. And for each delta lambda sample, you have to like compute a modeled state estimate at the time of every measurement in your batch. So you have like thousands upon thousands of propagations to do as part of that system. So for that, you need the STM to kind of enable that. But otherwise, we do numerical integration. Yeah. Okay, sounds good. Thanks.